Hello and welcome. Today, school's over. It's Thursday, and tomorrow will be class parties. So now you have a time frame as to when did I do these videos. Okay, I did not cover the end of Chapter 6 with you guys. I have to think in terms of timing. So I'm going to go over some of this. Standard enthalpy, enthalpies of formation. Okay, remember the idea about enthalpy. Enthalpy, we're looking at the total heat content of a system. And when we look at a system, we can look at it in terms of a chemical reaction. Think about it that way. So if we look at this, when we look at the standard enthalpy of formation, it's the measure of how much energy is released or consumed when we're having 1 mole of something that is created under standard conditions originally from its pure elements. Now, there is some symbols involved here. The symbol of the standard enthalpy of formation is delta H, and you'll see a little F there. That F is referring to the formation. So delta is the change in the enthalpy. Now, there is a degree sign as well. Don't be alarmed. It's just telling us it's a standard enthalpy change. So that's not really a big deal. The F, it's a reaction from that substance that's formed from its elements. So, there's got to be some formula to describe this. Well, if we look at the standard enthalpy change of formation, so we're looking at the total energy, not total energy, because remember, enthalpy is a combination of the internal energy of the system plus the work that it's doing. If we go back earlier in Chapter 6, so the delta H of the reaction is equal to the summation of the change in the enthalpy of the products minus the summation of the delta enthalpy, the delta H, the enthalpy of the reactants. Don't worry if you're not getting it right now. We'll move on with this, okay? And basically, this is what it's trying to say. The standard enthalpy change of formation is equal to the sum of the standard enthalpies of formation of the products, subtracted by the sum of the standard enthalpies of formation of the reactants. That's all that it's doing, okay? That's the idea behind it. So we're looking, again, enthalpy, the total heat content in the system. Now, let's move on here. Now, we've been talking about Hess's law, and you may remember we had our original equation we were looking at, and then we looked at different steps, different parts of the equation, because remember, when we're looking at the change in the enthalpy, we are looking at what did you start with and what did you end with. Think of the reactants to the products, or once upon a time and happily ever after, the beginning and the end. It doesn't matter what the path was like. Okay, that's a key thing to think about. So yeah, it's great if we know lots of reactions. You know, Hess's law is great, but you know what? There is actually a table for the standard heats of formation. And well, what is this heat of formation? Well, remember, we're dealing with 1 mole of something. We're not talking about you know, less than a mole or more than a mole. When we talk about those heats of formation, we're looking at 1 mole. So the idea is this. There is a table of standard heats of formation, and let me show you what that's going to look like. This is an example of enthalpies of formation. So for example, if we look at ozone, if we were to go and manufacture ozone, for example, we could take oxygen gas, okay, which has already got an enthalpy, and that's just 1 mole of it, is plus 249.17. Now this is telling us that it's absorbing the heat because of that positive sign. Now if we were to go and combine it with O2, we would get an O3 out of it. Now you'd say, but wait a minute, I don't see the O2 listed in there. Correct. There is a reason why, and that is when an element is in its stable form, its most stable form, it's going to have a heat of formation value, a standard enthalpy formation value of 0, nothing. So when we look at O, O2 and O3, which ones of those formations is the most stable for the oxygen? Well, you know that the one oxygen atom by itself has 6 electrons, valence electrons, and so it's going to be looking around for somebody, another atom to connect with. O3 is not exactly the most stable thing out there because it reacts quite easily in the atmosphere. All right. So O2 is the most stable form of the element, so that's why you're not seeing a value up here. It's 0. Okay. All right. So this is just an example of an enthalpy table for a moment. So if we look at it, all right, we can look at a simple chemical equation with the variables A, B, and C. Okay, so we got A plus B and we got C, and it's going back and forth. All right, now we have the standard enthalpy of formation values like this. So the enthalpy of formation value of, A is 433 kJs. For B, it's negative 256. Exothermic reaction, exothermic. And then for C, it's 523. Now, the equation for the standard enthalpy, okay, it is as follows. We're looking at the complete reaction. So here is our enthalpy. Here's the enthalpy of the entire reaction, this reaction here. And then we have the degree sign. Well, remember, it's a standard molar enthalpy because we're looking at 1 mole of something. And this is it. We know that C is our product, so we look at delta H formation of C minus the sum of delta H formation of A and the delta H formation of B. I know we're using letters, so perhaps it may be a whole lot better for us to use numbers and some equations that we can work with. I'll get to that in just a moment. Okay? I'm skipping this slide. I don't like it. Okay? But what we are going to do, we're going to go ahead and we can go ahead and use this one. Okay? So we're going to go ahead and we're going to work with this problem. And don't panic. You're not memorizing any of these enthalpy of formation values, those delta H of formation values. You're not. They're going to give you that information. I personally will give you that information. All right? I'm not going to mess with you guys on this one. Okay, so you know what? Let's take a look at this here for a moment. We're going to go and work with this particular... Well, you know what? Let me put a pause on that one. Let me work with a simpler equation because I think that's going to help you guys out a little bit more. Let's go with it. All right, we're going to get the notebook started. And all right. So let's take a look. I'm going to make my lines a little thicker. Oh, it's at the third thing anyway, so we'll go with it. All right. So let's take a look at something for else. So what is the delta H of formation, okay, our standard formation for CO2? So we're going to look at delta HF for carbon dioxide. Well, what do we need to have the formation of carbon dioxide? Well, we're going to have carbon here in the form of a solid plus O2 in the form of a gas. All right, and we're just going to have this go straight up to CO2 as a gas. We're quite familiar with it. Okay, so that's what we've got. Now, if we look at the formula, well, hold on. Let's get some information in here. So what would be the delta HF for the carbon? Here's the clue. It's in its most stable form, so that's going to be 0. 0 kJs per mole. Okay, oops, I should make that capitalized. Okay, and here is O2, and again, that's in its stable form. It's in its stable form, so again, that's going to be 0 as well. Now, our all the problem is going to be like this. Sorry, guys, not on the AP exam. Not a chance. You're learning this. Now we got CO2. Now CO2, we can sit there and say, okay, the value of the CO2 in the formation is negative 393.5 kJ per mole. So we have our delta H formations for carbon and oxygen and carbon dioxide. We have ourselves an equation. Okay, we have a formula, excuse me, where the delta H of the formation of this is equal to the summation of the delta H of our products minus the summation of the delta H of our reactants. Okay? So, we've got this information here, we've got this formula in here. All that needs to be done is plug this in. And you're saying, wow, really? Yes, absolutely. So in the end, it's going to be negative 393.5 kJ per mole. That's our product. Here, our delta H for the formation of the product, minus a big whopping 0 kJ, because you add these together, and it's 0. So our final answer for the delta H formation of CO2 is equal to negative 393.5 kilojoules per mole. So this is clearly an exothermic reaction. Why is that an exothermic reaction? Because that's a negative. That is a negative. Okay. Why don't we go ahead and let's try another one. Let's try another one here. Okay, let's look at delta formation for the formation of NO2. So that's what we're going to look at. We're now going to look at the formation of NO2. And of course, now the thing comes down to is, all right, how do we go about this? Where we need an equation, we need to get a reaction equation. Okay, well, let's take a look at it here for a moment. We need to determine, okay, what is the chemical equation that we have to have? Okay, we're going to have 2NO plus O2. Now, okay, it's going to be NO2. So that's our equation that we have for this. Whew. All right. Yeah, we're going to need some numbers. Absolutely. Well, O2 is automatically going to be 0, isn't it? Because it is an element and it's in its most stable form. Now, the NO2 is 33.18. And the NO is 90.25. So this is it. This is what we've got. And now we can go ahead and remember our delta H. Our delta H formation is equal to the sum of the delta H of our products minus the sum of the delta H of the reactants. Okay? So we have that formation and we have that formation. Now, we've got that. Now we got to work it. All right, well, let's take a look at our products. Well, our products here is 33.18 minus the summation of, now in this case here, it's not going to be 90.25, it's going to be 2 times 90.25. Because remember, when we gave that 90.25, that's for just one nitrogen monoxide, if you want to call it. One no. Okay? So it's going to be 2 times 90.25. We have to take that into account. Those coefficients, let's face it, we cannot escape those. All right? So we end up going and calculating all that, and in the end, we have ourselves negative 147.32 kilojoules per mole. So this is our final answer, dealing with the formation of NO2 given this equation that we started out with at the top. And if it once makes you, so that's what it would look like. All right. Let's do another one. Let's go ahead and do a let's go ahead and let's do that C2H5 OH, which is ethanol. It's a type of alcohol, not a drinking kind of alcohol. Plus 3O2 gets us 2 CO2 plus 3 H2O. Okay? So what are some of the facts that we have here? We know that this is plus 277.00 kJ per mole. This is going to be 0 because, again, this is oxygen in its most stable element. The carbon dioxide, it's going to be negative 395.5. Oh, sorry, 393. Hold on, let me erase that. So that's going to be negative 393.5. All right, and then the H2O is negative 285.8. Now, where did I pick up those numbers? There is the standard heat of formation tables. I do believe it would be in the back of the book. I also have one that I would give you guys on the day of the exam, but they're also out on the internet as well. There's different places. Sometimes the numbers are a little bit different. Again, they're going to provide that for you on exam day. I'm not particularly worried about that. Okay, so now why don't we go ahead and remember our formula. Our delta H total is equal to the summation of delta H products minus the summation of delta H reactants. Okay? So why don't we go ahead and let's plug this in. What is it going to look like? I'm not going to crunch out the numbers for you on this one. You can do that one on your own, but I am going to go ahead and plug in what we have here for the formula. So what are our products? Well, it's the summation of all our products, isn't it? So we have 2 of these CO2s. So what we're going to have here is 2 times negative 393.5 plus 3 times 285.8. Okay, remember those are the products. That's the summation of this. Those are the products minus our reactants. Well, what is our reactant? Well, we only have one of this ethanol. All right, so that's going to be C2H5. Oh, sorry, let me erase that. We're looking at the number, and that number is 277.0. Okay, so in the end, you're going to have a number that is definitely negative. It's less than 0. Guess what kind of a reaction that is? Exothermic reaction. Now, if you don't believe me, there are alcohol lamps out there where you can go and burn alcohol. You can take a, perhaps I'll show that as a demo another day, but not today and not right now. I want to do one more reaction with you guys. This one, oh my goodness, yeah, this is a fun one. This is definitely a fun one. This is working with thermite. Now, some of the guys out there may know what thermite is. Thermite, basically, it's aluminum oxide. And the thing about thermite with aluminum oxide, with it being aluminum oxide, if you combine it with iron, let me rephrase this. I'm sorry, I'm misreading. I have it here. The thermite